Hello and welcome. Welcome to the course on stochastic process and theory of queues. In this lecture, we will characterize the renewal process. We looked at renewal process as a generalization of the Poisson stochastic process. Basically, it is a counting process, but only the main nature is that the time duration between the occurrence of successive events can have a general distribution. It need not be exponentially distributed. Occurrence of each event is called as renewal because the process statistically renews itself and forgets history at those renewal times, and therefore we call it as the renewal process. So we will now characterize it and derive some important formula that can be stated for any generic renewal process. So we have a sequence of renewals or events that takes place. Let Sn denotes the time of the occurrence of the nth renewal. So at an arbitrary time 0, we say that a 0th renewal has occurred, that is 0th event has occurred. Then so S0 is equal to 0. We without loss of generality we define like that. Then the first event, when it occurs, the process renews for the first time. So that is what we call as the first renewal event. And the time it takes for the first renewal to take place has the exponential distribution with a random variable x, and that we will call it as the random variable x1. Okay. So the time duration between the first renewal and the second renewal is called as is a random amount of time, and we will call it as the x2. So x1, x2, x3 denotes random variables that define their duration between the first renewal and the starting time being x1. The second renewal and the first renewal we will call it as x2. The third renewal and the second renewal we will call it as x3, and so on. So we saw that x1, x2, x3 are IID random variables but has a general distribution, and it is also a common distribution which we will call it as x. The random variable will call it as x, whose CDF will call it as capital Fx of x, and the density function will call it as small fx. So with that we will see that S2, the time for the second renewal to take place, is the time taken for the first renewal to happen, and then plus the time taken for the second renewal to happen. So it is basically S1 is the time of occurrence of the first renewal. Add with that the time taken between the second and the first renewal, which is x2. So S2 is S1 plus x2. Similarly, S3 is S2 plus x3, and so on. So Sn, the time of occurrence of the nth renewal, is the sum of the xi's, I varying from 1 to n. Okay. Recursively we can write Sn is equal to Sn minus 1 plus xn. Now we know the characterization of x. CDF is called as capital Fx of x. Now what will be the characterization of Sn? Say the density function of Sn. So we know that Sn is equal to sigma I varying from 1 to n xi. The only thing that we know is that xi's are all IID random variables. So Sn is a sum of n IID random variables. Therefore the density function of Sn, which is denoted as small fSn of S, is the convolution of the density function of x1, x2 to xn. So here star circle is the convolution operator. So we convolve all the density functions 1 to n to get the density function of Sn. We know that when x1, x2 are all not only independent but also identical with a generic distribution x, it is the convolution of n identical density function fx convolution fx and so on. So n times convolution. So alternatively, if you know the Laplace transform of the density function, which we represent it as Lx of S, then the Laplace transform of Sn is the nth power of the Laplace transform of x, fx of S. This has to be capital X of S. But this way of formulating or characterizing Sn is a little difficult one, but that will completely give you the density function of Sn. In a similar manner, we can get the CDF of Sn and so on. But let us say we are not interested in the full characterization. We will just how to get the characterization in a much easier but alternate form. Let n of t denotes the process that indicates the number of events or renewals that has occurred till time t. Okay, and let us look at this process. And s of t, s of n represents the number, not t, s of n represents the time of the occurrence of the nth renewal. So they can be related. We know that n of t, the number of renewals that has taken place till a time t, is a integer valued one, monotonous, non-decreasing integer valued function of t. Because whenever a renewal takes place, n of t increases by 1. As t increases, it is like a staircase function, always non-decreasing. So whenever a renewal occurs, the process statistically renews itself and forgets history, and it can be treated as if it has started afresh from time t is equal to 0. Further, we will assume that the fx of x, when we characterize it, assume that the time taken for a renewal to occur, that is not equal to 0 with probability 1. Or in other words, if you look at the CDF of x, fx of x is less than 1 for all x equal to 0, for x equal to 0. Okay, so what it means is the CDF value is such that fx of x is not equal to 0, 1. If it were 1, it means that x takes a value 0 with probability 1. So this automatically implies that the mean value or the expected value of x is finite, it is not 0. Why we force this is, if it were 0, then renewals occur one after another in no time, and there will be an infinite renewal in any given time interval, however small it may be. We don't want to deal with such process. Anyhow, they are not the one which will characterize any natural physical events. So we will just enforce this condition, which in other words is the expected value of x is finite. Now two questions can be posed and answered easily. Can infinite renewals takes place in any finite time interval, or in an infinite time duration can only finite renewals can occur? Okay, so since fx of x 0 is less than 1, which means that the expected value of x is finite, probability that infinite renewals to occur in a finite interval, this can only happen when the expected value of the duration between two renewals is 0 for infinite renewals to take place in any finite interval. If it is finite, the probability of infinite renewals occurring in any finite duration is 0. Similarly, over an infinite duration, for only a finite number of renewals to occur means at least one of the renewals would have taken a realization of infinite, which is not possible if the expectation is finite. So over an infinite time duration, only infinite renewals can occur. Another one is, let us look at n of t, the number of renewals that take place, that has occurred until a time t. The condition that n of t equal to n, okay, implies that the time taken for n events to occur has to be less than t. So the time taken for n renewals to occur, only if it is less than t, the number of events at a time t can be n. If Sn is greater than t, the time at which the nth renewal occurs is greater than t, then at time t, the number of events cannot be equal to n. It has to be less than n. So this statement and this statement, okay, or this statement is important, is necessary for this. In addition, at a time t, if there are only n events, means the nth event should have occurred at a time less than t, and the n plus 1th event should have occurred at a time greater than t. Then only at a time t, precisely there would be n events. So both these two things are the necessary and sufficient condition for n of t equal to n. Alternatively, we can write n of t as the maximum integer n such that Sn is less than t. Okay, so the Sn is the time for occurrence of the nth event, nth renewal. It has to be less than t, and no other integer n should satisfy this. Okay, greater than n. For up to for n and less than n, this condition, the time of occurrence of the first renewal, second renewal, up to n renewals has to be less than t, and the n plus 1th renewal has to be greater than t. So it is the greatest integer for which the condition Sn less than t should be satisfied. Then only at the time t there will be exactly n renewals. Then let us look at the one in the limit n tends to infinity, Sn by n is equal to, in the limit n tends to infinity, Sn is nothing but sigma I 1 to n xi. So x1 plus x2 to xn by n. So this is nothing but the ensemble average of xi's, and that should be equal to E of x from the law of large numbers. So this should be equal to E of x, that is equal to mu x. So we can see that Sn by n converges to the mu x, which is the expected value of x as n tends to infinity. So in any finite interval, there has to be only finite number of renewals, and on an infinite interval there has to be an infinite number of renewals. Both these hold good. So some more thing that we can arrive at is n of t is greater than or equal to n, means at the time t, the number of events that has occurred is at least n. It is n or greater than n. That is what n of t is greater than or equal to imply. That is, at the time t, if n of t represents the number of renewals that has taken place, that is n or n plus 1 and so on. So at least n renewals would have taken place at the time t. That is what this statement implies. So this means that the time at which nth renewal has taken place, which we will call it as Sn, has to be less than or equal to t. So we have two statements which are equivalent. One connecting the process n of t and another connecting the process xn or Sn. So n of t greater than or equal to n and Sn less than or equal to t are equivalent conditions or events. So at the time t, the number of events is at least n or greater than n, and which can only happen when the nth event has occurred at a time less than t. If nth event has occurred at a time less than t, then it could be that n plus 1th event also might have occurred less than t, or n plus 2 event also, and so on. But at least n events would have occurred, and that is what this condition is. So we can write probability that n of t is greater than or equal to n is equal to probability that Sn is less than or equal to t. Now what we are interested is probability that n of t equal to n. That is, at the time t only n events have occurred. That can be written as probability that n of t is greater than or equal to n minus probability that n of t is greater than or equal to n plus 1. How? What is this event? N of t greater than or equal to n means at least n events at the time t. From that we are removing the condition at least n plus 1 events at the time t, which means exactly small n number of events at the time t, which is n of t equal to n. Look at this event. N of t is greater than or equal to n means at the time t there has to be n events, or n plus 1, n plus 2, n plus 3 all the way up to infinity. This is the event. Here there has to be n plus 1 event, n plus 2, n plus 3 and so on. So this event is a subset of this event, because this allows n or n plus 1 or n plus 2 and so on. Here this allows only n plus 1, n plus 2 and so on. N is not present in this, whereas it is present in this one. N onwards, here n plus 1 onwards. So this is a subset of this one. So if you look at a Venn diagram and then construct the events corresponding to this one, this event, this would be a subset of this one. Therefore, if you look at this event, you can find it from a set difference, and that is why this probability of this event can be subtracted from this to get this. So now we will make use of this condition. Probability n of t is greater than or equal to n implies probability Sn is less than or equal to t, and put it for these two things. Here we have to put Sn is less than or equal to t. Here n plus 1 is less than or equal to t. Therefore, probability that n of t equal to n is equal to probability that Sn is less than or equal to t. This comes from these two equality. From this one we can write probability that Sn plus 1 is less than or equal to t. So if S1, S2, S3 are all random variables, Sn is sigma I 1 to n xi. So we can construct the CDF of Sn. So this is nothing but the CDF of Sn, which will denote it as capital F Sn of t. This is the CDF of Sn plus 1. So we find probability that n of t equal to n is the difference of this CDF. One for the random variable Sn, another for the random variable Sn plus 1, both evaluated at the time t. So once we know this, we can construct this. Now we will also try to arrive at this n of t through other method or through different arguments. We can, to find probability that n of t equal to n, we can condition on the value Sn is going to take and then uncondition it, because Sn value is going to dictate on how n of t will take the value n. Once we know the Sn, we can tell something about this one. So we will condition on this one and then uncondition it. So if we condition by letting Sn to take a value equal to y, then multiply it by the density at that of Sn at y and integrate it over the entire domain of y, which is 0 to infinity. Because you know that xi's are all non-negative integer values, their sum Sn is also non-negative. So the domain of Sn is non-negative. That is why 0 to infinity we are doing. So now if you look at it, we will now look at the diagram to picturize what we are trying to do in order to arrive at probability n of t equal to m. So this is a time t. See, different events would have occurred. If you mark it along the time axis, the first event, second, third event are all, if you mark it, they will be at random points. And if you add up all these intervals, you will get the S. The time interval between successive markings is xi's. So x1, x2, x3 are all the time interval between successive marking. And if you put xn here, sigma I varying from 1 to n is Sn. So what we are interested in, at a time t, the number of events is equal to small n. So for that to happen, the nth event or renewal should have occurred at a time y, and no event should have occurred between y and t. Then only at a time t there will be exactly n renewals. That is the argument we are going to use to derive this. But supposing the nth event occurs at a time y, which is greater than t, then at the time t there cannot be n renewals. So if you condition y Sn to take a value y which is greater than t, no way n of t can be equal to n. So this, then that probability n of t to be equal to n given Sn equal to y, this probability will be 0 for all y greater than t. This cannot lead to this situation of n of t equal to 1, because the nth renewal has itself taken place here. How can there be n renewal at the time t? So this domain of y will not yield to this event. So we can split this integral as from 0 to t and t to infinity. And t to infinity, y cannot, if you take a value between t to infinity, then corresponding this probability will be 0. So we drop that domain. We only take it from 0 to t. That is, Sn has to be, can take a value y lying between 0 to t. That is one condition that is necessary. And in addition, no event should occur from y to t. Then there will be exactly n events at the time t. So this is a valid one. So we have to change it from 0 to t f Sn of y dy, and now what is this condition boils down to? No event between y and t, which means that if you look at the CDF of x, because this is where a renewal has taken place, nth renewal, and the time for the next renewal, that time has to exceed t minus y. So if you compute the CDF of x, okay, that is, if you compute the CCDF, that is the x which represents the n plus 1, the time between the nth and the n plus 1th renewal has to exceed t minus y. So if you, that is nothing but the CCDF, complementary cumulative distribution function of x evaluated at t minus y. So this becomes nothing but f bar of x at t minus y. So probability n of t equal to n is integral 0 to t this into f Sn of y. So this we will write it as it is, and this is nothing but f bar of x t minus y, which is the CCDF of x evaluated at t minus y. So f bar is nothing but 1 minus fx. Now let's just verify whether this formula will yield the correct formula for n of t equal to 1 for the well-known Poisson distribution, Poisson stochastic process. We know for the Poisson stochastic process, the time between successive events are exponentially distributed. So x is exponentially distributed, then x are all expo with, let us say, the rate lambda. Then fx of x, the CDF of x is 1 minus e power of minus lambda x for small x greater than or equal to 0. The CCDF of x is 1 minus fx of x, that is equal to e power of minus lambda x. So we know this. We should also know f Sn of y. What is Sn? Sn is x1 plus x2 to all the way to xn, where x1, x2 are all IID expo random variable with a parameter lambda. So sum of n IID expo random variable has a gamma distribution. So Sn is a gamma distributed random variable with a parameter lambda. So Sn, which is x1 to xn, and its density function is the gamma random variable's density function. Fsn of u is given by lambda e power of minus lambda u power n minus 1 by n minus 1 factorial. This is the gamma density function of gamma random variable with parameter lambda. So let us plug in this in place of Fsn of u y here, and for this we will plug in e power of minus lambda into t minus x evaluated at t minus y. Then probability that n of t equal to n is integral 0 to t. This is e power of minus lambda x at t minus u. So e power of minus lambda t minus u. And this is Fsn of y. So this lambda power n minus 1 comes out as lambda power n. E power of minus lambda t can also be taken out. N minus 1 factorial can be taken out. So remaining thing is integral 0 to t. This we can see that. See, look at e power of minus lambda into minus u is e power of plus lambda u, that cancels with e power of minus lambda u. So what remains here is u power n minus 1 into du inside this integral. So that will give you u power n by n between 0 to t. that n in the denominator can, along with n minus 1 factorial, gives you n factorial. And u power n by n between 0 to t will give you t power n minus 0. So the value is only t power n by n. So that t power n and lambda power n can be clubbed to get lambda t power n. So finally we have lambda t power n e power minus lambda t by n factorial. And that is nothing but the Poisson random variable with parameter lambda t. Lambda is the rate, t is the time interval. So this is the probability that there are n Poisson events occurring in a time duration lambda t with a parameter lambda t. Okay, so we have seen that this formula can be holds good for the well-known Poisson process, and it can be a very handy one for if you know any generic distribution. Because let us say if your generic distribution is uniform distribution, then you can easily find out the CCDF, this n-fold convolution of the density function and all these things, and apply it to get these things. So far what we have seen is continuous renewal process, which is a continuous time renewal process, okay, whose example is a Poisson process. We can also look at discrete renewal process. That is, if you conduct a sequence of trials and then every time an event occurs, the process may renew itself and become statistically identical with the starting time. Then we have got a discrete renewal process. Only thing is the time parameter is discrete. Okay, an example is a Bernoulli trial, wherein we conduct a sequence of Bernoulli trials, and whenever a success occurs, we may say a renewal has occurred. Okay, so when a success occurs and renewal has occurred. For example, if we could find a coin, in a case of the coin tossing, whenever an head occurs, a renewal has occurred. The process statistically renews itself. But we know that Bernoulli process is very similar to the random variable. Random variable is very similar to that of the if you take a sequence of Bernoulli trials, okay, and the time for the occurrence of a success has a geometric distribution, and that is very similar to the exponential random variable, because both of them have got memoryless property. So if you look at the time for the occurrence for the nth head or nth success is very similar to the Poisson process. In each trial it forgets history, but let us assume that it's as a discrete renewal process. Then we can see that if at the end of the 10th trial, if there are only 3 heads would have occurred, then again the condition is that the 3rd head would have occurred at a time less than the 10th trial, and no further head would have occurred till the 10th trial. So this is the probability that at a trial less than 10, there has to be exactly 3 heads, and between that trial and the 10th trial there has to be no further heads. This is easy to find if the probability of getting a success or head is P, and this is nothing but head should not occur. It is 1 minus P power so many number of this interval, 10 minus 7 and so on. And this is the probability that there has to be exactly 7 heads, 3 heads in 7 trials. And that 7 is a dummy index. It can vary from 3 to 10, because there is for at least 3 trials are needed for 3 heads to occur. So like that we can construct and arrive at a discrete random variable. Analyze a discrete renewal process. Okay, we will stop at this point. We will discuss more about renewal process and define a function called as the renewal function, which will be very useful in characterizing the renewal process.